Good morning, everybody. Welcome to Tuesday morning of Chem 1211 with your host, me, Dr. White. All right, what are we going to do today? Well, I'm going to do some mold problems because it's important that you practice it with me. And then after that, we'll do our lab. See, I'm all set up. And then we'll be done for today. I think we should be out by 10:30 or earlier. And that will give you plenty of time to do the lab. Don't forget, labs are due today that you did last week. And if you have any questions, don't forget my new office hours tonight at 6 to 7:15 and tomorrow night from 6 to 7:15, same Zoom login. All right. The other thing, I didn't have a chance, but I'll do it in the next day or two. I'll be posting changing it. The what's now listed as test number 2 review will now be test number 1 review, and I'll change the other reviews when we get in the coming week or two for each of the quizzes, and then that will help you. All right. Yesterday, I started talking about the mole in terms of mass or weight. And 1 mole of an element equals the atomic weight or mass in grams, and 1 mole of a compound equals the formula mass or formula weight. And I just realized I've got to open up one more thing. All right, and what I have here that I'll be reposting as test number 1 review or important information. This will be at the back of your exam, test number 1 that you'll have to take a COD. And where I've cut down on memorization, we're now discussing these 3 areas. 1, you should know. In the past, I'd say you have to memorize, but you should know 1 mole of an element equals the atomic weight of that element in grams. You should know 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of a compound is the sum of all atomic weights in that compound. The other thing, on the periodic table, the number underneath the chemical symbol is the atomic weight or mass. I use terms interchangeably. And remember, on all the future, on test 1, all the quizzes in my test 2, it will say, please use all atomic masses, the 3 significant figures. And that will help you make your life easier. Shh, don't tell anybody I'm being nice. So where does that take us? Let's look at the following. Everybody, thumbs up, people. Can you see the problem? How many grams AU on your screen?
Yes.
Thank you. I guess you're the only thumbs up, but you can just... All right, so how do we do this problem? Well, what are you being asked to find? Grams of gold. And on tests, I'd probably write out gold. and maybe not. And what are you given? You have 6.123 moles of gold. So once you have this, you never have to look at the problem again, and it makes your life easier. Well, the only number we have to start with is this. And we want to get the units of our answer to be this. And if there was some ratio that I could multiply my number I have to get to my answer, how do we do it? Well, it's time to use your good buddy, your good friend, unit analysis. And how do you use unit analysis? Whatever units you're trying to get to, go on top of the ratio. Whatever your units you're trying to get rid of, go underneath. And I'll write those in. And where do I get these numbers for the ratio? Well, you look at important information and says 1 mole of an element equals the atomic weight of that element in grams. 1 mole of an element equals the atomic weight of that element in grams. Well, first of all, we need the atomic weight of gold. And gold AU right here, 196.967. Well, that's 6 significant figures. Rounding that off to 3, keep the 1, keep the 9, keep the 6. The next 9 used to round off, that's 5 or higher. You drop all those numbers and the 196 becomes 197. So we know atomic weight of gold equals 197 grams. Because that, we're gonna, the atomic weight, 1 mole equals that in grams. And from important information, we know 1 mole of an element equals the atomic weight, and I'll abbreviate it, of the element. And therefore, let me remind you, if you have A equal B, there are 2 ratios you can derive from that. And these are not equal, they're separate ratios. So we know 1 mole of an element, in this case gold, equals atomic weight, which right here we figured out is 197 grams. I don't have to write that again. And now, before I pick up my calculator, we're going to check, do I end up with the right units? And how do you do that? You remember anything divided by itself equals number 1, meaning it's crossed off, it's gone. So here we have moles of AU divided by moles of AU. That becomes number 1. It's gone, deleted, and we're left with the only units, grams of AU, which is what we want. So now I'm going to multiply and divide. First of all, I'm going to turn on my calculator, clear it. I have 6.123 times 197. And my calculator gives me this number in scientific notation. And remember, on test 1 and all the rest of the quizzes and test 2, it will say, just like on test 1, please use proper significant figures for all calculated answers. And if we look at this one, this is 4 significant figures, all non-zero numbers are significant. That's 3 significant figures. And the 1, that's an exact number. It's part of the definition. Therefore, it plays no role in determining significant figures. Here we have 4, here we have 3. When you have multiplication and division, your final answer should have the same number significant figures as the lowest number of significant figures you have in your calculation. And now it's the hard math time, which is smaller, 4 or 3. Hopefully you all pick 3. So now we have to round this off to 3 significant figures. Keep the 1, keep the 2, keep the 0. Those are my 3 significant figures. And use the 6 to round off. That's 5 or higher. I'm going to drop all this, increase that by 1. So if I want 6.123 moles of gold, I'll have to weigh out that amount of gold. 1.21 times 10 to the third, or 1,210 grams. And that's how you do it. Oh, this was fun. Let's do another one. All right, question is, how many moles of water, you should know H2O is water, is 38.5 grams of water. So I'm going to ask you right here, what are you being asked to find and what are you given? And when you're done, give me a thumbs up. All right, so what are we being asked to find? How many moles? Oh, I forgot the many. How many moles of water? And so we're trying to find moles of water. And you don't have to put the S for moles. Usually you don't. And what are you given? How much weight? 38.5 grams of water. And once we have this, you never have to look at the problem again. So the only thing we have to start is this. And if there was some conversion ratio, what units do I want my answer? Grams of water. And now we use our good buddy, our good friend, unit analysis, and whatever we're trying to get to goes on top of the ratio, and whatever we're trying to get rid of goes underneath. And I'm talking about the units. So I'm going to write those in. Grams of water, moles of water. And now the question is, where do I find a relationship between moles of water and grams of water? Well, we look at important information, and you see, first of all, 1 mole of a compound, and water is a compound, is equal to the molecular weight of that compound in grams. What's the molecular weight of the compound? Oh, look, that's an important information too. And that's the molecular weight of a compound is the sum of all atomic weights in that compound. So I'll rewrite this part of it here. Just realized the way I was going to write it might confuse some people. So let me fix this. Molecular weight in grams. So 1 mole of compound equals the molecular weight in grams. And the molecular weight is the sum of all atomic weights in grams. So first of all, from this, we can say 1 mole of water equals the molecular weight in grams of water. Oh no, we don't have the molecular weight of water. So we've got to figure it out. Water has 2 hydrogen, 1 oxygen. And we need the atomic weight of hydrogen and oxygen. And where do we get that? We go to our periodic table, and hydrogen to 3 significant figures. Here's the H underneath. That would be 1.01. Oxygen, O, over here, atomic number 8. That's not what we want. We want the number underneath it, which is the atomic weight, and 15.999 to 3 significant figures is 16.0. And you know something? I'm going to make this 8 points, not 5. And so this is 1.10. These are the atomic weights. This is 16.0. Multiply it, you get 2.02. You have 16.0. And now we're going to add it up because that's the sum of all atomic weights. And that would be 18.02. However, that's not the right atomic weight. For this addition, you have the same number of significant figures to the right of the decimal as the number that has the fewest significant figures to the right of the decimal. This has 2, this has 1. I have to round this off to 1, keep this, use that to round off. That's 4 or less, I'll drop it. So the correct answer here is the atomic weight of water is 18.0. Now I could have done it, now that I have all my numbers in, before I pick up my calculator, I'm going to check my units, and remember, anything divided by itself equals number 1, meaning it cancels out. And therefore we have water here. And I did it backwards. Hold on, unit analysis saved me. I did this backwards. Where I made the mistake, and Dr. White makes a mistake once in a while, and luckily unit analysis helped me. I put the wrong units here. And unit analysis, you notice I'm turning red because I'm embarrassed. I should have put moles water.
So what we want, we always put on top, right? And what
Yep.
we don't want on the bottom. Okay.
Right, and that's where where I made my mistake was right there. And now I've got it right. For every 1 mole, we have 18.0 grams. And this helped me see I made a mistake. So unit analysis, always check that your units cancel out. I just did and found out I made a mistake. But anyways, now grams divided by grams of water cancel out, and I'm left with the right units. If I paid attention to what I wrote, I wouldn't have made that mistake. Bad, Dr. White. And now I can pick up my calculator, clear it. And my calculator gives me this number. Give myself some space here. 2.13888. There are more eights. Moles. Doesn't say that on my calculator. And remember, it will say on test number 1, please use proper significant figures for all calculated answers. And this is 3 significant figures. This is 3 significant figures. This is 1 significant figure. What am I saying? This is exact number. This is Dr. White makes 2 mistakes today. That's the last one. And therefore, the answer should have 3 significant figures. I'll give you 3 seconds to round this off to 3 significant figures. I'll give you more than that. And the answer is keep the 2, keep the 1, keep the 3. Use the 8 to round off. Is that 4 or less or 5 or higher? Hopefully I'll pick 5 or higher. Drop that, increase that by 1. And the correct answer is this. And that's how you do it. Oh, let's do another one. Make sure I get it right this time. All right. NaOH is sodium hydroxide. It's a very important chemical used in the United States and actually worldwide in the chemical industry. Now, the question is, how many grams is 1.763 times 10 squared moles of sodium hydroxide? I'll let you try first. First of all, write, what are you being asked to find? What are you given? And when you've done that, give me a thumbs up. Again, I'm only asking you, what are you given? What are you being asked to find? All right, let's get going. How many grams of sodium hydroxide? That's what we're trying to find. What are we given? Are we given this number? How many moles of sodium hydroxide we have? And now the only number we have to work with is this. Keep an eye on Dr. White. I already made 2 mistakes today. Sorry.
Maybe you need a coffee.
Really. Where's my 4-leaf clover when I need it? All right, now, what units should go there? I'll let you try that. We're going to do this stepwise.
So that's gonna be grams?
That would be grams of sodium hydroxide, because this is what we're trying to find. Now, I'm going to let you use your good buddy, your good friend, and this is a rhetorical question. I'll answer it. What units go on top and bottom here? And when you figure that out, give me a thumbs up. All right, my turn. And it's time to use your good buddy, your good friend, unit analysis. Whatever we're trying to get to, and I checked again, that's the right units for the answer, goes on top. Whatever we're trying to get rid of goes underneath. And now I'll write those in. And notice moles of NaOH divided by moles of NaOH will cancel out because anything divided by itself equals number one, meaning it's gone. And I'm left with grams of sodium hydroxide, so I'm on the right track. Now, how do we proceed? Where do we get a relationship between moles of a compound and grams of a compound? And if we look up here, someone nicely wrote 1 mole of a compound equals the molecular weight of that compound, and the molecular weight in grams equals the sum of all atomic weights in grams. So we know 1 mole of a compound equals the molecular weight. Oh no, we've got to figure out the molecular weight of sodium hydroxide. And that's the sum of all atomic weights. There's 1 sodium, 1 oxygen, 1 hydrogen. Well, where do we get those atomic weights? From your friendly neighborhood periodic table. And for sodium, underneath Na, you see 22.989. And therefore, if we round that off to 3 significant figures, that will be 23.0. Hydrogen is still rounded off to 3 significant figures. It is 1.01. And oxygen, the 3 significant figures, is still 16.0. So the sum of the atomic weights is the molecular weight, and I have 23.0. There's only one, so I don't have to worry about multiplying. Oxygen is 16.0, and hydrogen is 1.01. We'll add them up together, and keep an eye on me. We get 40.01. Now, when you add, you have the same number of significant figures to the right of the decimal point as the number with the fewest significant figures. This has 1 significant figure, this has 1, this has 2. Which is the lowest number? Hopefully you pick 1. So we keep the 0, use the 1 to round off. That's 4 or less, I'll drop it. So the molecular weight of sodium hydroxide, the sum of all atomic weights, is 40.0. So I'll put that in there. And now I've already checked my units. This cancels out. And it's time to pick up my calculator, clear it. Remember, second key, double E. And my calculator gives me this number. But remember, you should use proper significant figures for all calculated answers. This is a multiplication division. This has 1, 2, 3, 4 significant figures. This has 1, 2, 3. Remember, zeros at the end with a decimal point are significant. This is an exact number and plays no role. So which is the lower number, 3 or 4? And the answer is 3. And rounding this off to 3 significant figures, keep the 7, keep the 0, keep the 5. Use this to round off to 2 as 4 or less. I'll drop it. And the correct answer here So if I needed these amount of moles, I can weigh out this amount of sodium hydroxide in a balance. And that's the importance of being able to do this. And we'll see more. All right, let's do one more. All right, the question is 8 points. How many moles ammonia? Remember, NH3 is ammonia. Very important chemical used in the United States. It's a gas at room temperature, but under pressure, it's a liquid. How many moles of ammonia are 125.6 grams of ammonia? And we're going to do this stepwise. It's called in teaching fading prompts. First thing I'd ask you to do is find out what are you being asked to find and what are you given. Let's do this stepwise. And when you're done, all I'm asking you right now is to find how many moles are what are you being asked to find and what are you given? I just gave it away. All right. You're asked how many moles of ammonia. So we're trying to find moles of ammonia. What are we given? This number. And since this is the only thing we have to start with, I'm going to start with this. Now, what units are we trying to get to? Write that in, and once you got it figured out, give me a thumbs up. All right, and the answer is right here. Moles of ammonia. Now, if we had a magic ratio that can convert this to this, what would go on top and what would go on bottom unit-wise, not numbers, just units. Your turn. All right, my turn. And it's time to use your good buddy, your good friend, unit analysis. Whatever we're trying to get to, the units go on top. Whatever we're trying to get rid of, they go underneath. And now write them in. And now the question is, where do I find a relationship between moles of a compound ammonia and grams of a compound ammonia? And if you look at important information, test number 1, this will be given to you in the last 2 pages. 1 mole of a compound equals the molecular weight of that compound, and the molecular weight of that compound is the sum of all atomic weights. So, knowing this, 1 mole of a compound equals the molecular weight, I can come back here and say 1 mole of a compound equals the molecular weight of the compound in grams. Well, oh no, we've got to figure out the molecular weight of ammonia. Now, ammonia, the molecular weight of ammonia is the sum of all atomic weights. And in case you ever forget that, that's an important information test number 1, which you'll be given. So we need 1 nitrogen and 3 hydrogen. And what does that mean? 1 times the atomic weight of nitrogen, 3 times the atomic weight of hydrogen. And earlier we figured out this is 1.01. Let's look up nitrogen. If you look at your periodic table, nitrogen, chemical symbol N, has an atomic weight of 14.007. To 3 significant figures, keep the 1, keep the 4, keep the first 0. Use the second 0 to round off. That's 4 or less. I'll drop that into 7. The atomic weight of nitrogen, the 3 significant figures, is 14.0. 1 times 14.0, 14.0, 3 times 1.01 is 3.03. It's the sum of all atomic weights, so I add it up. I get 17.03. However, we're not done. Addition, you get the same number of significant figures to the right of the decimal as the number that has the fewest. This is 1, this is 2, which is the smallest number, 1. So we keep the 0, that's the first one, to the right of the decimal. Use the 3 to round off. It's 4 or less, I'll drop it. So the molecular weight of ammonia is 17.0 grams. And now I can put that in there. And before I pick up my calculator, remember, grams of ammonia divided by grams of ammonia cancel out, and we're left with what we're trying to get to. So now I can happily pick up my calculator, clear it, and my calculator gives me this answer. And that's a lot of significant figures. Remember, when you're multiplying or dividing, you have the same number of significant figures in your answer as the number you're multiplying, dividing, that has the fewest significant figures. This number has 4 significant figures. Remember, every non-zero number is significant. This number, 17.0, 0 at the end after a decimal is significant, has 3 significant figures. Therefore, this is the lowest number. We need to round this off to 3 significant figures. So I'll give you some time. Why don't you round it off and give me a thumbs up when you're done? All right, my turn. Keep the 8, keep the 9, keep the 7. That's my 3 significant figures. Next number used to round off. And you notice I used the double squiggly line underneath. And that's 4 or less. So I'm going to drop all this. And the correct answer is this. And that's how you do it. And let's go through this again to remind you how I did it. We're asked how many moles of ammonia are 125.6 grams of ammonia, NH3 is ammonia. And I like to write out, and it's helped me and it's helped many, many students What are you being asked to find? And I use a question mark to identify that. Moles of ammonia. What are you given? Grams of ammonia, 125.6. This is the only number I can start with. I want to get to what units? Well, my answer says I'm trying to get up here to moles of ammonia. And if you had a ratio conversion factor that can convert grams of ammonia to moles, what would that ratio be? Use your good buddy, your good friend, unit analysis. Whatever you're trying to get to goes on top of that ratio. Whatever you're trying to get rid of goes underneath. And where do we get these numbers? From the fact that 1 mole of a compound equals the molecular weight in grams of that compound. MW is shorthand for molecular weight. And the molecular weight of that compound is the sum of all atomic weights. AT period, WT period is short for atomic weights. So we need to figure out what's the atomic weight, what's the molecular weight of ammonia, and it's the sum of all atomic weights, 1 nitrogen, 3 hydrogen, the 3 significant figures from the periodic table, the atomic weight, the number underneath the chemical symbol is 14.0, the 3 significant figures, and hydrogen, which we've done before, is 1.01. Multiply it, 1 times 14.0, 14.0, 3 times 1.01, 30.03, add them together. Remember, when you're adding, you get the same number of significant figures to the right of the decimal as the number you're adding that has the fewest significant figures to the right of the decimal. And this has 1, 2, so I round this off to 1, pass to the right of the decimal, 17.0, 1 mole of a compound per 17.0 grams, do the math, round it off, and that's that. And if I look at the clock, now would be a good time to take a 5-minute break. I'll see you in 5 minutes, and we'll come back and do our exciting lab for today. See you in 5. And that would be 9:50. Time to get going. All right, it's lab time. And don't forget, when you do your lab, you should wear your safety goggles and you should wear gloves, and they give you an apron. You can wear that too. For today's lab, you're just dealing with water, so I don't think you need an apron, but you should be safe. All right, let's look at today's lab. Give me a second while I close some stuff. All right, thumbs up, people. Do you see metal calorimetry on your screen? Thank you. All right, today's lab deals with the concept of heat. And you measure heat changes with a device called calorimeter. Now, today's lab, here's some of the stuff you'll need. And when we talk about heat, that's energy, thermal energy caused by atoms and molecules moving. Right now, atoms around you, in you, are moving, and molecules. If you've ever felt the wind on your face, you're being hit by molecules. Well, turns out when we talk about this, there's something called the kinetic molecular theory. And atoms and molecules are always moving. In gases, there's a lot more space. In solids, they're pretty much stuck, moving very close together. Now, a property that is associated with thermal heat is temperature. And temperature and heat are related, but they're not the same quantity. Temperature is the average kinetic energy of a particle in a material. That's average kinetic, where heat is the total energy. Now, there's a concept called specific heat. And this is a property of materials. Water has specific heat. Today, you'll determine the metal ring specific. I think there's steel. And there's different units. And for example, water has a specific heat of 4.184. J is joules, a measure of energy per gram degrees C. And that's 4.184 joules of energy is required to raise the temperature of 1 gram of water 1 degree C. And this is the relationship that shows that. Q, which is energy, equals the specific heat, C sub S, times M, the mass, the weight, times the difference in temperature. If you have a temperature change, delta T, the first symbol is the Greek letter delta for difference. That's the final temperature minus the initial one. Now, this whole thing, equation 1, comes from an area called thermodynamics. And probably one of the toughest undergrad courses for chem majors when I was getting my bachelor degree at IIT, it's called thermodynamics, but chem majors call it thermo. And when we say thermo, because it's one of the toughest courses you take ever. It's really tough. And when I took it, the professor, I can still remember his name, Dr. Wood, he actually wrote the book we were using. And it was a small brown book. And boy, was it a tough course. It really was. I think I got a B in that course when I got a B once in a while. But I did a lot better than everybody else. Most people got C's or D's in that course. It was tough. Well, anyways, thermodynamics, otherwise known as thermo, deals with the heat and energy of molecules and atoms. All right, so we have this, and what we're going to do is use calorimetry. It's a way of measuring the amount of heat transfer in a closed system. Now, calorimeters are insulated closed systems that you can put two things together to measure heat transfer. Now, some of the calorimeters, like at the National Bureau of Standards, cost tens of thousands of dollars. Guess what? And they're very well insulated. Our calorimeter does not cost tens of thousands of dollars. It's a cup, insulated styrofoam cup. Something was dirty in there. And for today's lab, I'm going to make a change. Listen up. They talk about cutting one of the cups to put inside the other. Don't cut it. Just take this one, put it in there, you're set. Now, these are light. Even with water, it can knock over. Take your plastic beaker and use that as a holder for your cups. Now, one of the things you'll need to do is take a piece of cardboard. I got this from a box, but if you want, you can probably, let's see if it fits. It does. The box cover from the box you got from your kit, you can use this for your cover. I didn't. Now, you want to cut a piece of cardboard like about this big enough to cover the hole, and then you'll punch a hole inside there. And what's that for? Your thermometer. And remember, your thermometer's glass, be careful with it. And it's got this little holder to keep it from rolling off the bench. But there's a good thing. When you're putting it in here, you can use that to adjust the height of your thermometer in your cup. So you'll have a setup like this. Let's get back to the lab. Now, it turns out you're going to be working with metal washers, and they gave you way more than you need, unless we're going to use some of these in a later lab. I don't know. And you'll need 6 of them. And here's the washers. And what you'll be doing is measuring heat transfer from the metal to water that will be in your calorimeter. And equation 2 tells you the water heat will be equal to minus, don't forget that minus, the metal heat. The minus tells you metal will be releasing heat to water. Now, Q equals equation 1. So if we go to equation 3, the specific heat of water times the mass, the weight of water, times the change in temperature of the water is equal to minus, remember that minus sign, the specific heat of metal, C sub S, times the weight of the metal, times the change in temperature. And you're going to be determining this lab what is C sub S metal, the specific heat of the metal you're using in your rings. Ooh, they're loud too. So here's the materials you'll be using. They also give you string to use. I don't know why you need the ruler, but let's go through this. Don't forget, make sure you wear your proper personal protective equipment, safety goggles. You're going to be working with boiling water. Don't touch the pot when you're heating it. Don't touch the boiling water. Don't touch the rings after they've been in boiling water. They're hot, you'll burn yourself. So be careful. And as they say here, things you'll need is a stovetop, oven mitts, or a pot holder, small pot, tap water, cardstock, or like I did, scissors, a heat resistant spoon that could be wooden or other material, and some way to time something. All right, now in the preparation, they talk about cutting the foam cups. Don't do that. You don't have to. Trust me, I'm a chemist. Did that work? What I did and what you should do for this lab, take one cup and put it inside another. Now, they don't tell you, but I would use the plastic beaker as just a holder. You'll need a piece of cardboard, and you can use the box top. And notice how this covers the top of mine. You'll want to punch a hole near the center. I was a little off on the center, that you can put your thermometer in. Now, what you'll also need, while I was late, here's one of my old Calphalon pots that I use all the time. I've had this since about, wow, 1980. These are really well made. And I have one, it's not wooden, but you'll be putting it like this. And this will allow you to wrap string around here and put the washers in there, metal washers. Now, the first thing you have to do, don't forget, you'll need your balance, is take your cups, put it on your balance, tare it, zero it, and put in 40 grams of water. If you're a little over or a little under, that's okay. Just record it. Instead of 40.0, you're going to be, say, 39.95 or 40.6, but record that. Then put the water that's in here in the cup. You can put it in here now. And what you'll do is cut lengths of string. They say about 18 inches. I didn't do that, but you should. And then what you'll need to do, I've already put the 40 grams of water, and then you'll pour that, put the water, and you can measure it right in the cup itself. And you'll measure the temperature of the water, put the cover, put the thermometer in. You know how to read a thermometer. We went through that a previous lab. And while you're doing this, you should get a pot of water. This doesn't look like one of my pots, but I know where it comes from. And it should be about 2/3 full. And you don't want a real tall stock pot. Dr. White, who likes to cook, I have a 4-gallon stock pot when I make chicken soup and stuff like that. And I have a huge freezer and I fill it. But I also have a 8-quart, that would be 2-gallon stock pot, but you'll want to use a smaller pot like this. And you'll fill it about 2/3 water. And to make things go quicker, Dr. White knows how to work in the lab and get out quick. What you'll do is take one ring and weigh it and put it aside. Take 2 rings and weigh it and write it down, and then do 3 rings. And what you'll do, all right, where did I hide my string? I didn't cut it, but you can. When you're doing the one washer, you'll take the string like this. You'll take your spoon, wrap it around a couple times, and then carefully with an oven mitt, so you don't burn yourself, put it in here like this. Then you're going to let it sit in the boiling water for 2 minutes. You'll take it out, quickly put it into the cup with the water, 40 grams, and then you didn't tie any knots. So you can go like this. Pull the string. Practice before you do it real time, like I just did. Take your thermometer, put it in. Every once in a while, carefully swirl it. And after about, and keep an eye on the temperature. And you may have to pick it up a little so you can read the temperature, but make sure the bulb is in the water, and it should be. And you'll watch the temperature, and over a 2-3 minute period, you'll record the maximum temperature. That will be your final temperature of the water, your initial temperature before you put the ring in there, and you're done with ring 1. You'll do the same thing. Put this in boiling water with the string, like I showed you. Don't tie knots. And I would, before you start the second run, take this, dump it out, put in 40 more grams or whatever, record it, get ready, boil for 2 minutes with the string in there, using this, put it immediately in there. Before you did that, you measured the temperature of the water the second time, and then after you put the rings in there, you keep on looking, you swirl this every once in a while, you'll look at the temperature and record the maximum temperature. And you'll repeat the same thing with 3 rings. Hold on. With 3 rings. And you'll weigh it. Well, you've already weighed them. You'll put the string in there, put it in the boiling water, 2 minutes. Fresh water in here, take the other rings out, measure the initial temperature, and then take these with the string, put it in there and measure it. So you're going to be doing 3 different runs. The difference is the weight of the metal, 3 rings, 2 rings, and 1 ring. All right, now let's look at the table. Let me first of all be careful and put this away so I don't break it. Remember, wear proper eye protection since I'm not handling any chemicals right now. I didn't put on my goggles. Let me clean some space here. And feel free to go back and look at that part of the video I just did that I'll post later today, so you can watch it again if I went too fast. Now, let's look at what we've done. We've done the procedure, and for each run, for 1 washer, you'll have the mass, and I'd mass away all 3 at this one, then do a second one before you start anything. You'll have the initial temperature of the water before you add the rings, the final temperature, which is the maximum. Delta T water is final minus initial. And here's the specific heat of water. Now, you'll have the mass of the, here's the mass of the water you weighed with the cup each time you do a run. Then each ring, you should do 1, 2, 3, weigh them. Now, this lab assumes, which I'll talk more about it when we get into gases, that the boiling point of the water you're using is 100 degrees C. And let's use that. Now, the final temperature here of the metal is the final temperature of the water. The final temperature of the metal is the final temperature of the water. And what you're going to do is calculate the specific heat of the metal for each run. How do you do that? Good question. Thank you. You're welcome. From equation 3, we have specific heat of water times the mass of the water times delta T of the water equals minus, don't forget that, the specific heat of the metal times the mass of the metal times the delta T, change in temperature of the metal. Now, in this lab, we're trying to solve for the specific heat of the metal. I'm not going to go through the steps. I've done it for you. And here's the equation you'll use to determine the specific heat of the metal. Let me just show you something and I'll come right back to it. Where it asks the specific heat of the metal in column 1, 2, and 3. You'll use that equation and I'll call that equation 4. And then you'll average the 3 values and get an average. Here's the literature value, and you need to calculate the percent error. So let's go back and look at all of this. This is equation 4, and you'll use this. This is given to you, 4.187. This is the weight, approximately 40 degrees. Now, delta T water equals temperature, the maximum temperature, final water, minus the temperature before you put in the rings, initial temperature. Now, delta T metal equals the final temperature of the water minus 100 degrees, because that's the temperature of the metal in the boiling water you started with. This is going to be a negative number, which is why we multiply that times minus 1 to get a positive number, which this always is. So don't forget this minus right here, and this is going to be negative. If it isn't, you made a big mistake. Trust me, it's going to be less than 100, the final temperature of water. So what you're going to be doing is calculating this, the specific heat of the metal, and then you're going to take an average. Remember, add the 3, divide by 3, and then you need to find a percent error. And that's equal to the absolute value of the metal average minus the metal literature value, and I'll show you that in a second, divided by the metal literature value. And actually, I should put here, hold on, let me do something clearer. this value here, this is the average of the specific heat minus the metal specific heat, the literature value, divided by the specific heat of the metal, the literature value. And then this is the absolute value, it's a positive number, times 100. And that's how you get percent air. Now, what's that C sub M lit? Well, you're given that in the lab. And see where it says specific heat of steel, carbon steel, and it's 0.50. That's the number you should get. We call that the literature value in chemistry. But guess what? Are you using $10,000 calorimeters? No. So do I expect you to get this exact number? No. Would I get that exact number with the equipment we're using? No. And that's why you're going to have to figure out the percent error. All right, everybody see on your screen right now, metal calorimetry student name, date. Thank you. All right, now this is posted in Blackboard. Here's the table you should fill in from the previous one. Why they made a mistake right here and here, I don't know why they have it crossed off or whatever, but I've just gone through all the numbers you have in here. I've shown you how to calculate the specific heat of each metal. I've shown you how, well, the average is these three numbers, add and divide by 3. And I've shown you how to do the percent error. Now, what you also have to do are the questions at the end. 1, 2, 3, and you've noticed Dr. White added 2 of his own, 4 and 5. And that's today's lab. Let's go through this one more time, the math. What you're being asked to find is the specific heat of the metal, C sub M. You'll find you're given this number, C water. You'll figure out the mass of the water for each run. It should be about 40 grams. And you'll measure the initial temperature of the water with your thermometer. And after you put the metal ring in, you'll see what's the maximum temperature it goes to. Should only take about 2-3 minutes most. Remember, every once in a while, carefully stir it a little after you put the rings in, or ring. And then you'll divide that by the weight of the metal, which you've measured, and the delta T of the change in temperature of the metal. The delta T water, change in temperature water, is the final temperature of the water minus the initial. The delta T of the metal is the final temperature of the water minus 100 degrees C. That will be a negative number. And where you have to have the percent error, that's C sub M average minus the literature value, 0.50, divided by 0.50. This is an absolute value times 100. And with that, that's today's lab. I'm done. Any questions before I say goodbye? All right. I'm done for today. Remember, tonight I have my office hour from 6 to 7:15. If you have any questions, stop by. And we had a good morning. Hopefully you've learned some things about moles. You now know how to do the lab. And with that, I'll say, Gang gesund. Bye now.